We can now move on to section 6.2. Section 6.2 talks about the properties of a power series. So it's what we did in section 6.1, and then we're just going to talk about the properties of this stuff. Before I start this, what I like to always say, and I've said it throughout this whole class, is that this stuff is going to look way harder than it really is. The notation of like the sums and then having a constant and then having powers and having roots and just all of this stuff, the notation can sometimes look really gross, which makes you think these things are harder than they really are. So what I want to say is nothing I'm going to show you in section 6.2 is new. Nothing is new. The notation is new. The definitions may be new, but what we are actually doing is all math you have already done in either Calculus 2, sometimes in Calculus 1, but some of this stuff even goes back to like high school math. It just looks really bad. Okay, so preface that. Don't freak out. It's easy. Section 6.2 is one of the easier things we are going to do in this whole class, okay? But the notation is gross. So just be warned, we are going to be fine. Of course, if anything doesn't make sense, let me know. But for the most part, I think you guys are going to be fine. This is particularly true in this very first part right here. All of these are rules we already know, okay? For example, the first one right here, the power series. Oh, and what it says at the start right here is that if the sum of Cn xn and the sum of dn xn go to f and g. So this is equal to f, this is equal to g. If that's true, then the sum of Cn xn plus dn xn is equal to f plus g. Duh. You know what I mean? Because what I'm saying is this plus that. We already said this is f. We already said this was the g. So it makes sense. If I add them up, it's f plus g. Nothing new there. That's something we already knew. Same thing down here. bx to the m. If that is in front of something that I already know, see, I already know this, right? This is something we already know is equal to f, right? Then I can just factor out this b stuff. I can just factor it out front and times it by x. We did that in section 6.1. We just didn't use the notation. We did that whenever we had the example that was like x squared over 4, 1 minus x squared over 4. We just factored this out and made it x squared over 4 times 1 over 1 minus x squared over 4, because this, we said, was the sum of 1 over, just kidding. The r was x squared divided by 4, so x squared over 4 to the n times x squared over 4. And then we just put this in here instead. But that is exactly what happened. This guy messed us up, so you can just factor that out. That's all rule number 2 is trying to say. So don't overthink it. Even though it looks hard, don't overthink that. Same thing with this one right here. The sum of Cn times bx to the m to the n. So I'm plugging something else in here. I can just do the function at that point, which is exactly what we did here. Because the rule we had used here was that 1 over 1 minus r is the sum of Rn. That's the rule we had used here, right? Well, instead of an r, I had some stuff. So just plug in that stuff. That's what number 3 means. So nothing is new. No new tricks, no new rules. It's just putting them in a notation that's more mathematically correct. That's what it is, okay? So looking at example 1a. One A says, use the power series representation for 1 over 1 minus x to construct a power series for each of the following. So 1a is the function 3x over 1 plus x squared. And again, what it says is use what I know about 1 over 1 minus x. Well, we know this is geometric 1 over 1 minus r, right? So we know this is the sum of xn. Again, because it is geometric, where my r is equal to x. So I know this, okay? Well, let's look at what I have right now and see how I can use this guy, okay? So first things first is instead of a 1, like what I know, I have a 3x. So what I can do is just factor out 3x. So 3x times 1 over 1 plus x squared. That takes care of my 1. I now have that. And then again, down here I have 1 minus x, so I want this to be a minus. So that's going to be 1 minus negative x squared. So now it looks a lot like this. The only change is that I have negative x squared instead of an x. So I factored out 3x, so put 3x out front times the sum of, again, I normally have an x. I have negative x squared there instead, so replace x with negative x squared. That's it. That's it. This is exactly what we already did. In fact, in my opinion, writing it out like this just makes it way harder because it was way quicker just to see this as A and this as R and then write it out. You know what I mean? Instead of trying to factor out and do all that kind of stuff. But this is what they mean. Once again, I can find the interval of convergence. My r is negative x squared. Absolute value of that has to be less than 1. That means negative 1 is less than negative x squared is less than 1. The minus sign is going to flip everything. Square root. I can't take the square root of a negative. I did it again. So negative x squared is always going to be a negative. So take the negative away when I do the absolute value. It's going to give you that. Then take the square root and you get plus or minus 1, which is how you do get that. So the interval is going to be negative 1 to 1. The radius is 1 because it's half of my length. And B is going to work the same way. We're just going to have to think about it a little harder, but still the same thing. F of x equals 1 over x minus 1 times x minus 3. And again, what I want to use is what I know about 1 over 1 minus x. That's what I want to use. So what I want to do is I want to make this look like this. But the hard thing is I have two factors here, which I don't really like, right? So if only there was a way I could rewrite that to where they're each their own term. Oh wait, we can. We learned this a while back, right? This is partial fraction decomposition. So I know I'm going to have something over that, something over this, and I need to figure out what they are. So for the a term, I would need to times this by x minus 3, which would give me ax minus 3a. This one I would need to times it by x minus 1, so bx minus b. That has to be equal to 1 from up here. So that means a plus b has to be equal to 0, and negative 3a minus b has to be equal to 1. Let's solve for a here. Subtract b gives you a equals negative b. So this means negative 3 times negative b minus b equals 1. Negative 3 times the negative 3 times the negative b is going to be positive 3b minus b equals 1. 3b minus b is 2b equals 1, which means b is equal to 1/2. Plug that back in here, gives me a is equal to negative 1/2. So negative 1/2 plus 1/2, like that. And now the idea again is that I want them to look like this. So on top, I just want a 1. I have negative 1/2 there, so factor out a negative 1/2 times 1 over x minus 1 plus, same thing again, factor out 1/2 times 1 over x minus 3. Let's see for each, so what I want to do then is I want to do this work for each of these. So I'm going to do it for this guy and for this one over here, individually, okay? So first things first is this one over here. I want 1 over 1 minus x. I have 1 over x minus 1, which is close, but on the bottom here, my terms are switched. So think about how I might be able to switch those. Pause it really quick and think about it. How I'm going to switch those is I'm going to factor out a minus sign. Is going to make those terms switch. Again, because I want 1 minus x, and they're flipped right here. So factoring out a negative would make this positive 1/2, and then I could do 1 over 1 minus x. Boom. So helpful. Same thing over here, though. I want these switched because, again, the x should be the last term, so I need to switch those. So do the same thing. Factoring out a minus sign right there gives me negative 1/2, 1 over 3 minus x. Am I good? No, because, so this one right here is good. It looks exactly like it. I'm happy there. This one, though, has a 3 when I really want a 1. So I need to factor out a 3 on the bottom right here to make it a 1. So 1/2, this one's fine. I'm happy with that one. Factoring out a 3 on the bottom would make it 2 times 3, which is a 6 now because I'm factoring out a 3. 1 is 1 over. Factoring out a 3 from 3 gives me 1. Factoring out a 3 from x gives me x over 3. So then now I'm good. Both of these, look how this one does, so I'm good. For the first one, 1/2, this is literally the same, so I'm good there. 1/2. Sum from n equals 0 to infinity of x to the n, minus, I have a 1/6 out front, sum n equals 0 to infinity. What's being subtracted here is x over 3, so that's x over 3 to the n. That's how I find that sum. So now I need to find the interval of convergence for this. So I need to do that for both of them, okay? So doing it right here, my r is equal to x, which means the absolute value of x has to be less than 1. The absolute value means it could be -1 or +1, and I'm good. That one is solved for x. Do the same thing over here. R is x over 3, so absolute value of x over 3 has to be less than 1. The value means I can do -1 or +1. Times 3 gives you -3 less than x less than 3. So the problem here is which one of these is right. I got two things. It doesn't make sense for a series to have two, so we have to figure out which one is right. So pause and think about it really quick. Which one do you think am I going to use? The answer is I need to figure out which one works for both of them, right? -3 to 3 would include -2, it would include 2, it would include 1/2, it would include all those things that are not included here. So they would work for this half of it, but not this half of it. So this one isn't really helpful because it gives me more than this one does, which means there are numbers for x in this guy that wouldn't work over here. So I don't want this one. I want that one. Again, because the numbers in here work for both of them. So the interval of convergence is going to be -1 to 1. The radius is half of my length, so just 1. Let me know if that doesn't make sense, though. Example number 2. It's even easier than all that was. Example number 2 says for each of the following power series, find the function representation and the interval of convergence. So now I want to go backwards. I'm going to give you the ending. Tell me how I got there. Okay, that's what I want to do now. Even less work than those few we just did. So example 2. A, we're taking the series from n equals 0 to infinity of 2 to the n, x to the n, and I want to write it as a function, something like these were. All right, so all of these have been geometric, so I want to figure out how I can write this as a geometric. Remember, geometric series look like this. So notice something about this. Notice both of these two terms I have right there have a power of n, right? So what I can do is I can just write it as 2x to the n. Again, because both of them have a power of n. So I look like this. My a is equal to 1. My r is equal to 2x. So I can just write it. Remember, it's a over 1 minus r. A is 1. R is 2x. That's it. That's all I've got to do. Okay. I still need the interval. Remember, our rule is the absolute value of r has to be less than 1. Our r was 2x. Absolute value means it could be -1 or +1. Divide by 2, and you get 1/2. Getting ahead of myself. Divide by 2, -1/2 is less than x is less than 1/2. So the interval is from -1/2 to 1/2. Remember, r is half of my length. My length is 1. Divide that by 2, and your radius is 1/2. That's it. Then example 2b is done the same way. Sum from n equals 0 to infinity of 1 over 3 to the n times x to the n. Do this one the same exact way. Since this is a 1 up here, I could write it as x to the n over 3 to the n. Both of those have a power of n. So I can write that as x over 3 to the n, which now means I look like that, with a equal 1, r equal x to the or x over 3, which means my function is going to be a, which is 1, over 1 minus r, which is x over 3. Now a function normally doesn't look like this. This is a mess, right? So since I have x over 3, I can multiply everything by 3, which will give me 3 over 3 minus x. Try that again. Like that. Do the same thing we have been doing. Remember the absolute value of r has to be less than 1. R is x over 3. Absolute value of x over 3 has to be less than 1. Absolute value means it could be -1 or +1 times by 3. Yeah. So the interval of convergence is -3 to 3. Radius is half of my length, which is 3. Let me know if any of that doesn't make sense. So this next part of section 6.2 is where students are always like, what is going on? But it's something we have done in math forever. So let's look at it, use the notation and everything that they want. Then I'm going to explain to you why it's something that you have done a bunch of times. So this is how to multiply power series. Suppose that the power series, which is the sum of Cn xn, and then another one that is Dn xn, suppose those both converge to the functions f and g respectively over I. Then let's make this new thing that is En. En is equal to C0 dn plus C1 dn minus 1 plus C2 dn minus 2 plus dot 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 up until Cn minus 1 d1 plus Cn d0, which is equal to the sum of Ck dn minus k. Then doing the sum of Cn x to the n times dn x to the n is the same thing as the sum of this En x to the n, which converges to f of x times g of x on I. This is called the Cauchy product. This looks complicated. This is multiplication like what you have always done throughout all math. Okay? They just had to put it in proper mathematical wording. Okay? But what this is trying to say is, imagine I was doing like x squared plus x plus 1 times 3x squared minus 4x plus 5. Remember, how I do this is I do this first term times everything in here. So I would do x squared times 3x squared and get 3x to the 4th. That would give me negative 4x cubed. That would give me plus 5x squared. Then do the same thing for x. This would give me 3x cubed. And on and on and on. That's what this means. We are doing the same thing as that. This is just using proper notation since it doesn't ever stop. You know, like right here, I have a last term. This is my last term. This is my last term. These are going to go on and on and on forever and ever and ever. So it had to notate it a certain way just to make sure that's clear. But it's the same thing as what I'm doing here. So don't overthink these next two I'm fixing to do. So like example number 3, for example, multiply the power series representation 1 over 1 minus x, which we know is equal to the sum of xn because it's a geometric, which is equal to, if I plug 0 in to start with, I get 1. Then if I plug in a 1, I get x to the first, so just 1. Then so just x. Then if I plug in a 2, I get x squared. If I plug in a 3, I get x cubed. And then I would get x to the 4th, x to the 5th, on and on and on. With the power series representation 1 over 1 minus x squared, which again is geometric, so then we know it's the sum of x squared to the n, which is equal to, plug 0 in, I get 1. Plug 1 in, I get x squared. Plug in 2, I get x to the 4th. Plug in 3, I get x to the 6th, and on and on and on. So what I want to do is I want to multiply those so that I can get a power series representation for 1 over 1 minus x times 1 minus x squared. Okay. So again, what this means, the series that I want is the series for 1 over 1 minus x, 1 minus x squared. That's what I want. However, that's not in a form I can work with, right? Because the only one I can work with is a over 1 minus r. Since I have two things here, it doesn't work. But what I can do is this is like saying 1 over 1 minus x times 1 over 1 minus x squared. So I can do the series for this, which I can do, and times it by the series for this, which I can do. Number 1, because I know how to, but then also number 2, they give me those. They tell me those right here. 1 over 1 minus x is the sum from n equals 0 to infinity of xn. 1 over 1 minus x squared is the sum from n equals 0 to infinity of x squared to the n. And they give me the first few terms of those two things. 1 over 1 the sum of xn is equal to, this is on our note sheet, so hit pause or read your note sheet if you are taking my class. 1 plus x squared plus x cubed plus a bunch of terms. The sum of x squared to the n is 1 plus x squared plus x to the fourth plus x to the sixth, on and on. And what I want to do is just like what I said. First term here times every term over there. Then do the same thing for the next term, everything. Next term, do everything. Next term, do everything. So leave yourself a lot of room. 1 times everything in here. 1 times 1 is 1. 1 times x squared is x squared, blah, 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 on and on. So 1 times all of those is going to be 1 plus x squared plus x to the fourth plus x to the sixth, on and on. Now do x. X times 1 is x. X times x squared is x cubed. X times x to the fourth is x to the fifth. X times x sixth, x to the seventh, on and on. Move on to x squared, which will give you x squared plus x to the fourth plus x to the sixth plus x to the eighth. Then do x cubed, x to the fifth, x to the seventh, x to the ninth, on and on. Then combine like terms. The only constant that I have is a 1. So 1. X squared, I have an x squared here, then I have an x squared there, and I will not have any other x squareds because the only way I could have gotten it is from doing 1 times the x squared here, and then again from doing the x squared times the 1 here. So it can only happen twice, it will not happen again. Ooh, I just realized I forgot the x's. So the x will only happen once because the only way I can get an x is by doing this x times this 1. There's no other way I can get just plain x. Because I could do 1, but there's nothing over here to get me just x. So the only way is x times 1, so there's only one x in there. Now, I have an x squared here and an x squared here, and it won't happen again. So that's just 2x squareds. X to the third, it happened here and it happened here, and it won't happen again, because the only way I could have gotten it is from doing x times x squared right here, and then from doing x cubed times 1 right here. There's no other way I can get it. So it only happened twice. X to the fourth would be next. 1x to the fourth here, another x to the fourth here. It's going to happen again because my next term is x to the fourth. Do that times 1, so that will happen 3 times. And you're probably seeing the pattern. 1, 1, 2, 2. So this will be 3, 3. 4, 4, and on and on. So this is the power series representation for 1 over 1 minus x times 1 minus x squared. And you can just stop there. I'm not going to have you make it a sum. I'm not going to do that. Just leaving it like this is great. On a homework or on a test or that kind of thing, I will say something like, find the first 5 terms of, and do this, and just find me the first 5 terms, and that's fine. So again, this is math you've already done. There's nothing calculus-y about this. This is math you already know. Example number 4 is going to work the same way, except they don't give you as much stuff, but it's stuff we already know, so we can work it out. Multiply this series 1 over 1 minus x, which we know is the sum of xn, by itself to construct a series for 1 over 1 minus x times 1 minus x. So for example number 4, the function 1 over 1 minus x times 1 minus x. Again, this isn't a form I can do. The only form I can do is a over 1 minus r. This isn't that, but I can write it as the product of 2 that are. So this is the product of 1 over 1 minus x times 1 over 1 minus x, which I know a little bit about, right? 1 over 1 minus x is the sum of x to the n. So I'm doing that twice. So the sum of x to the n, plug in 0 and you get 1. Plug in 1, you get x. Plug in 2, you get x squared. Plug in 3, you get x cubed. On and on. Then the same thing here, because it's the same. So for this one, 1 times 1 is 1. 1 times x is x. 1 times x squared is x squared. 1 times x cubed is x cubed. Then do the same thing for x. X plus x squared plus x cubed plus x to the fourth. X squared times all of this. And then x cubed times all of it. On and on. And of course, this will keep going and going and going. Combining like terms, that's the only x. Or that's the only 1. So just 1. X happens here and there, and then it won't happen again. So just 2x. Have x squared, x squared, x squared, and then it won't happen again. So 3x squared. X to the third will happen 1, 2, 3, 4 times, and it won't happen again. And then keep on. You can see a pattern here. 1, 2, 3, 4. So then it'd be 5x to the fourth, 6x to the fifth, 7x to the sixth, on and on. Once again, on like a homework or that kind of thing, I won't have you find the sum. You can just write it like this. That's perfect. So if that doesn't make sense, let me know. Okay. Now, I want to show you something cool. Okay. What do you notice about this? Let's look at this, and what do we notice? Pause and take a think about what each of these terms kind of looks like. Okay. Notice here, each of these looks like a derivative. 1 is the derivative of x. 2x is the derivative of x squared. 3x squared is the derivative of x cubed. 4x to the third is the derivative of x to the fourth, and on and on. So we said this was the power series for 1 over, that's basically 1 minus x squared, right? Notice this. What is this the power series of? What is this the power series of? Well, it looks kind of like the power series that I just wrote up here, except I don't have a 1, right? But it looks a lot like this. That is the power series for 1 over 1 minus x. So the power series representation for 1 over 1 minus x, the derivative of that, the derivative of the power series for 1 over 1 minus x is equal to the power series for 1 over 1 minus x squared. Well, what else do you notice? 1 over 1 minus x squared is the derivative of 1 over 1 minus x. So what does this mean? What this means is if there's a power series that I want to find that's not in a form I can do, but if it's the derivative of one that I can do the one I can do and just take the derivative of that. That's it. So instead of working all this out, I could have just done that straight up. That's what we talk about on the next page. When differentiating or integrating the function representation of a power series, we can simply differentiate or integrate each term of the power series. So let's use that for example number 5. Complete the following. A says use the power series representation f of x equals 1 over 1 minus x, which we already know is the sum of xn, which we already know is 1 plus x squared plus x cubed, to find a power series representation for 1 over 1 minus x squared. So I'm realizing now that's the thing I just told you, but let's pretend I didn't, and let me show you what I mean, okay? I should have read ahead just a little bit just to make sure I wasn't spoiling anything. So 5A, what they're saying is use what I know to find something I don't know. So what we want is the power series representation for 1 over 1 minus x squared. Now this is in a form that I cannot do because the only form I can is a over 1 minus r. I have 1 minus x squared here. So that's not in this form here. So on first glance, it's not something I can do. But notice 1 over 1 minus x squared is the derivative of 1 over 1 minus x. Let's check that just so that y'all know that I'm not trying to lie, okay? Let's find the derivative of this, okay? The derivative of this, I would use the quotient rule, right? Remember the quotient rule is on top, low, d high, which means I would take my denominator, the derivative of my top, which is 0, minus high d low, so take my numerator, which is 1, times the derivative of the denominator, which is negative 1, over the denominator squared. Look at what happens here. This is all equal to 0. Negative 1 times a negative 1 is positive 1 over 1 minus x squared. So this is the derivative of that. I know the power series representation of that. We know 1 over 1 minus x is the sum of x to the n, which is 1 plus x squared plus x cubed plus x fourth, on and on. So since I want it for the derivative, I can just take the derivative of this. So the power series for 1 minus x squared, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x to the third is 3x squared, the derivative of x to the fourth is 4x cubed, on and on, which is the same as what I got on my last one. So this is just another way. That's my answer. So once again, I recognize this was the derivative of something that I know. So do the one I know and then take the derivative. That's all I did. 5b is doing the same thing, except for b, we want to find the power series representation for 2 over 1 minus x cubed. So very clearly, this is one I can't do because I have 2 over stuff cubed. So it's not in the geometric form that I want, right? But is there one that I already know that I can use? So let's pause and think about this. Is there a function of which this is the derivative that I can use? The answer, this is the derivative of 1 over 1 minus x squared. Let's check that and make sure. We could write this, instead of doing the quotient rule, we could write it as 1 minus x to the negative 2. Use the power rule, bring the power down, take the derivative, for taking the derivative, bring the negative 2 down, decrease my power by 1. By the chain rule, I have to times this by the derivative of the inside stuff, which is negative 1. Negative 2 times the negative 1 is just positive 2. 1 minus x to the negative third is like saying over 1 minus x to the third. So there we go. So the one that I want is the derivative of one that I know. This is what we did in example A. This is example B. This is the one we did in example A. We said that 1 minus 1 over x squared was 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth, on and on. So to do the one that I want, I just have to take the derivative, and that's it. The derivative of 1 is 0, the derivative of 2x is 2, derivative of 3x squared is 6x, derivative of 4x cubed is 12x squared, derivative of 5x to the fourth is 20x to the third, and on and on. So if the function that I want to use is the derivative of one that I know, do the one that I know and then take the derivative of it. Same thing would go for if the function that I want to know is the antiderivative of one that I know, then do the one I know and then take the antiderivative of that, which is what I'm going to do in example 6. Example 6, for each of the following functions f, find the power series representation for f by integrating the power series for f prime and find its interval of convergence. So I want to do for f of x, this is example 6a, f of x equals the natural log of 1 plus x. So this is clearly not a form I can do because the only one I can do is a over 1 minus r. This is nowhere even close, right? But is this function either the derivative or the antiderivative of one that is in that form that I like? Well, remember the derivative of the natural log is 1 over that stuff, right? Which would then put me into the form that I want. So take the derivative of that. The derivative of the natural log of 1 plus x is 1 over 1 plus x. This is in the geometric form, right? Because remember the geometric form, it's like this. Except this would be minus a negative x, right? So this is the sum, because it's like saying 1 minus negative x, of negative x to the n. So remember, this always starts at 0. Plug in 0, negative x to the 0 is 1. Plug in a 1, you get negative x to the first, which is just negative x. Plug in a 2, the negative x squared is just positive x squared. Following that pattern, negative x cubed, positive x to the fourth, negative x to the fifth, on and on. So that's all fine and good, but I want it for the natural log. So since this was the derivative, I can now go backwards and take the antiderivative to help me out. So the antiderivative of 1 is x. Antiderivative of negative x squared over 2. Antiderivative of positive x squared plus x cubed over 3. And then continue going on for all of my terms. On and on and on. This is the one that I want. Again, because I can do it for the derivative, so do that, and then take the antiderivative to go back to the one that I want. One more example is 6b. We're going to do the same thing for inverse tangent of x. Remember that the derivative of inverse tangent will be, because my first thought is I look at this and that's nowhere near the form that I want, right? But remember that the derivative of inverse tangent is 1 over 1 plus x squared. We learned that, I believe, calculus 1. Yeah. This looks a little bit like the geometric form, except I want minus, so minus negative x squared. That makes this the sum of negative x squared to the n. Plugging in 0 gives me 1. Plugging in 1 gives me minus x squared. Plugging in 2 gives me plus x to the fourth. Continuing that pattern gives me that. So that's for the derivative. So now I got to go backwards, take the antiderivative. The antiderivative of 1 is x. Antiderivative of negative x squared is negative x cubed over 3. Antiderivative of x to the fourth is x to the fifth over 5. And continue on doing that. And there we go. The very last thing of this section says that a function cannot have more than one power series representation. All that this means is that once you find it, this is the only one. You can't find more that'll work for this thing. So that's all that says. Remember, if any of that doesn't make sense, reach out and let me know. I will be happy to help you out.